Today we're going to continue solving more problems involving torsion by starting with a new topic called power transmission. And the idea behind this is that if we have torque applied to a shaft and that shaft is rotating at a constant angular velocity, we can calculate the power. The equation is power is torque times angular velocity. P is what we're going to use for power, T is torque, and omega is angular velocity. Angular velocity must be in radians per second. We aren't often given radians per second, so what if we are given units of RPM? That's revolutions per minute. We'll need to convert this by multiplying by 1 minute in 60 seconds, so that's a form of 1. That'll let us cancel the minutes. We will also need to convert revolutions to radians. You might recall that there are 2 pi radians in a circle. So if you go around 1 revolution of a shaft, you've gone 2 pi radians. So this is the conversion we need in order to go from RPM to radians per second, which you'll sometimes need to do in your homework problems. Once we have our angular velocity in radians per second, we'll multiply it by our torque, which for SI units, here's what power is going to look like. Power is a watt in SI units, and a watt is 1 Newton meter per second. So you see how that'll work out? Since if our torque has units of Newton meters and our angular velocity has units of radians per second, we think of radians as being like a dimensionless thing. We will end up with Newton meters per second. There's no additional conversion needed. Now, English units are not so friendly. The English unit of power is a horsepower, and a horsepower is 550 foot-pounds per second. Not a friendly conversion factor, one that I have to look up every time I need to use it. You need your torque in foot-pounds, your angular velocity in radians per second, and then you will additionally, once you get your power in foot-pounds per second, you'll need to use the 550 to convert to horsepower. Let's do an example. My example that I'm going to start out with is this solid steel shaft that goes from A to C, has a diameter that we're given, 25 millimeters. It's also in the figure. And it says it's supported by smooth bearings at D and E. So for torque purposes, these bearings, we're going to assume they allow the shaft to totally freely rotate and don't provide any torque. And so the torque is all going to be happening where the motor connects to the shaft, as well as where these gears connect to the shaft. We are told that the motor delivers 3 kilowatts of power, and it is turning at 50 revolutions per second. So we're going to need to convert that into radians per second at some point. And we're told that the 2 gears each remove 1 and 2 kilowatts of power. So this is pretty common for a power problem. They'll give you an input power from a motor and output powers at each of the gears. And these output powers have to exactly add up to the input power. We are then supposed to find shear stress in the shaft in between A and B, and again between B and C. To do this, I like to first draw a free body diagram where I replace those powers with torques. So drawing a free body diagram of this shaft, the motor is delivering some amount of torque, some torque at C that's equivalent based on the speed it's rotating at to 3 kilowatts. You get to pick whichever direction you want to draw that torque. You can draw it clockwise, counterclockwise, does not matter. Now the output torques though at A and B have got to be in the opposite direction. So there's TB and there's TA. So if you drew the input this way, your outputs need to both go the other way. We'll need to solve for TA, B, and C in just a second. And we know that if you sum torques now, TA plus TB minus TC has to sum to 0. And they will, because our output and input torques were already balanced. This isn't really a great free body diagram because I kind of forgot about the bearings. So just for completeness, let's draw what those bearings would do. We've got a pair of bearings. We're not going to draw any reaction moments at those bearings. We're only going to draw the reaction forces, which will be perpendicular to the shaft. So I'll have a D, we'll call Z upward, and DX outward, assuming the shaft is lined up with the y-axis. And then we would also have ZX. And let's assume one of these is a thrust bearing and the other one is not. So if it is my thrust bearing, you would have also EY on there. And that'll work for a free body diagram. We don't actually care about any of these forces because all we're really doing for a torsion problem is summing torques about that axis. So summing torques about the y-axis has to be 0, and we get that TA plus TB minus TC has to equal 0. Next, we need to figure out what the torques are. So you'll remember our equation is power is equal to torque times angular velocity. Solving for torque, it'll be power divided by angular velocity. I know I'm going to need to convert that angular velocity, so why don't we do it right away? Our angular velocity was given as 50 revolutions per second, but I need to convert revolutions into radians, and there's 2 pi radians per 1 revolution. The revolutions cancel, and we get our angular velocity, and that number comes out to be 314.2 radians per second. Let's do the torque at C. That is going to be our power at C, 3 kilowatts, and divide by that angular velocity, 314.2 radians per second. A kilowatt is a kilonewton meter per second, because a regular watt was a newton meter per second, so times 1,000, a kilowatt would be a kilonewton meter per second. The kilowatts cancel, the 1/seconds cancel, radians is treated as dimensionless here, and we're going to get our torque in kilonewtons times meters. So the torque at C comes out to be 9.55 times 10 to the minus third kilonewton times meters. Well, I don't really want a 10 to the minus third with a kilo, so let's convert that to newtons. This is 9.55 newton meters. Then we do the other two. And doing that, you will get that the torque in B, you just replace the 3 kilowatts with 2 kilowatts, and you get 6.366 newton meters and 3.183 newton meters. So we get those by converting the kilowatts of power into torques using the angular velocity of the shaft. Now, in order to find stress, I need to know internal torque. So to find internal torque, I'm going to do free body diagrams of cuts. So let's do a free body diagram where we cut section AB somewhere. So I'm coming up here and I'm cutting somewhere between A and B, like right here, for example. If we do that cut and just keep part of the shaft, I've got the gear, and then here is my cut open edge. The gear has TA on it that I just calculated, and the internal torque would be the torque in section AB. It's an internal torque. That is going to equal TA. If you sum torques here, you get that TAB is just equal to TA. How do we get shear stress? The max shear stress in AB, we're going to use our TC over J, or T rho over J. The torque is 3.183 newton meters. The rho, that's the radial distance from the middle of the shaft, plug in the biggest radius. So the shaft had a diameter of 25 millimeters. So that radius would be half of that, 12.5 millimeters. 12.5 millimeters is 0.0125 meters. And now I need J, polar moment of inertia. Well, that is, for a solid shaft, pi over 2 times the radius, 0.125 meters, to the fourth power. See how my units are going to work out? I have meters squared in the top, meters to the fourth in the bottom, so I'm going to end up with newtons per square meter, which is pascals. This number comes out to be 1.037 times 10 to the 6th newtons per square meter, which is 1.04 megapascals, if I round to 3 sig figs. We have one more section to find the stress in. It's in between B and C, so I need to cut somewhere in between B and C and keep either everything to the left or everything to the right. So let's do this free body diagram. We have to go all the way to the end of the shaft where A is, and then we have B on here. I'm not including the bearing at this point. I'm just including torques because all we're doing is analyzing torques in this problem. So what's applied here? We had a torque at A, that direction. We also had a torque at B, that direction, and then probably in the opposite direction, we'll have the torque in segment BC. So the torque in segment BC is going to equal torque at A plus torque at B, which will be the 9.55 newton meters. Tau max in section BC will be T rho over J. The torque is bigger, it's 9.55 newton meters, but the radius is the same, 0.125 meters, all over pi over 2 times 0.0125 meters to the fourth. 3.11 times 10 to the 6th pascals, or 3.11 megapascals. And that's it for that problem. The new thing for today was taking those powers in kilowatts and converting them into torque. The other new topic for today is angle of twist. If you apply a torque to a shaft, how much will it twist? Our governing equation we're going to end up with is torque length over polar moment of inertia times G shear modulus. Let me define all of these letters for you. This phi, Greek letter phi, is our angle of twist. We're using the Greek letter phi. T is torque, L is length, and J is that friendly polar moment of inertia again. And G is a material property. That is the shear modulus of the material. Remember when we did material properties, E is Young's modulus, G is shear modulus. So I want to just remind you quickly that we previously were dealing with axial loaded members. And when we did axial deflection, we had an axial deflection equation that was actually quite analogous to this. The axial deflection of a bar was force length over area times Young's modulus. So do you see how they're similar? In torsion problems, you have a torque. In axial deflection problems, you have an axial load. How much you twist or how much you deflect is directly proportional to how long the bar is. Inversely proportional to how kind of big or round it is. When it comes to axial deflection, what matters is the cross-sectional area. For twisting, it's a different area property. It's polar moment of inertia that matters. And then in axially loaded bars, what matters is that Young's modulus. It's sometimes called a tensile modulus for things that are being pulled in tension. Whereas when we're twisting bars, we're really putting them into shear. So that's why we end up with shear modulus in here. What kind of units are we going to get? So TL over JG, let's look at all those units. Torque is something like Newton meters in SI units. Length is meters. J is meters to the fourth, and G is newtons per square meter. So what's going to happen to those units? The newtons cancel. I've got meters squared on the top of the fraction with meters to the fourth divided by meters squared. Well, that's meters squared on the bottom of the fraction. So all of those meters are actually going to cancel out. We get dimensionless. Well, I called it an angle. What's our dimensionless angle? Radians. So when you plug everything into this equation, whether you're in English units or SI units, you're going to get something dimensionless, or you should if you convert all of your units correctly. Dimensionless means radians. Sometimes the textbook's going to ask you, what is the angle in degrees? There are 2 pi radians in a whole circle, and there are also 360 degrees. So you may occasionally need to pull this out and make a conversion factor to go from radians to degrees when you're done. But the equation itself will not give you degrees. The equation itself will give you radians. This is your general angle of twist equation. Do you remember what we did with axial deflection over here when we had more complicated things? We actually said for more complicated things, delta was the sum of all of the FLs over AEs. And to do that, we had to be very careful about which sections of the bar were in tension versus compression. So in this case, we will also sometimes do phi is equal to the sum of all of the TLs over JGs. So to do that, we're going to need a sign convention. The sign convention is we have to call something positive and something negative. What we do is using your right hand, if you point your thumb out on either end, you're going to end up with an internal torque that looks like that. This way on this end, it's got to be exactly equal and opposite on the other end, but in both cases, your thumb is pointing out and away from the end. We are going to define this as positive internal torque, and guess what negative is? It's exactly the opposite. To get negative, you need to point your right thumb in on each end, and so your torques are going to end up being that way. This is negative internal torque. Let's practice it. Here's my example. We are given this shaft. It has 3 torques applied to it, and it is fixed to the wall at A. We are told it is solid with a diameter of 20 millimeters. We're given material properties. It's made of A36 steel, and just to save us some time, I looked that up. It is 75 gigapascals for the shear modulus, and we are supposed to find the angle of twist at point B. I guess I better label my points on here. If A is back at the wall, we're going to call B the point out here at the front, C is there, and D is there. Our governing equation is going to be that phi is the sum of all of the TLs over JGs. And for this problem, it's just a single shaft that is solid, same diameter everywhere. So J does not change on this shaft, and neither does G because it's all made of steel. I can actually simplify this just a little bit by pulling the 1 over JG out in front and multiplying then by the sum of just the torques times the length they act over. I also need to add some dimensions here. This first section is supposed to be 800 millimeters. This second section is supposed to be 600 millimeters. And this last section is supposed to be 200 millimeters. So we have lengths. We can calculate J because we know the diameter. We know G. So what I need to figure out are the internal torque. Should we go ahead and calculate J though before we do that? J is pi over 2 times the radius to the fourth. That'll be pi over 2 times 10 millimeters, 010 meters to the fourth, which comes out to be 1.571 times 10 to the minus 8th meters to the fourth. So we'll use that later for our J for the whole problem. But I really need though are the internal torques for these segments with their proper sign. So to get internal torques, you're always going to take a cut. So let's do a free body diagram cutting between B and C. Don't cut at B or at C, cut in between them, because that internal torque is going to be exactly the same value anywhere you cut in between, but then it's all of a sudden going to change at C and have a step change. So don't cut at C. When you do your cuts, always keep everything all the way out, in this case to the end. Acting on the end in this direction is 80 Newton meters. So my internal torque, I am going to draw it as positive. So right thumb pointing out of the cut open face, which means you're rotating that way. There's your TBC. And now we sum torques. Summation of the torques has to be 0. And what we get is, since TBC and 80 Newton meters are in the same direction, TBC is actually minus 80 Newton meters. Keep that negative sign, it's important. So when we sum in this equation right here, we need the ones that are positive to be positive and the ones that are negative to be negative so that we get the right answer when we're done. That's one torque. We need 2 more of them. So let me take a different color. We need to cut in between C and D. So let's do a free body diagram, cut between C and D, but you do want to keep the material all the way out to the end. Don't just chop it off here or you'll tend to make more mistakes. So chop it and keep everything to the end. So my chopped off shaft is a little bit longer this time. It has 80 Newton meters applied there. It has 20 Newton meters in the opposite direction. And then again, I'm going to draw this in the positive direction. Positive just always means right thumb coming out of the face. And here will be my torque in between C and D. I again need to sum the torques and set it equal to 0. I've got 80 Newton meters and the torque at CD in one direction and 20 Newton meters in the other direction. So those sum to 0, and I get TCD is minus 60 Newton meters, so also negative. And I need to do one more cut because I have one more section. This cut is going to be in between D and A. So free body diagram, cut between D and A. There's my even longer shaft. There's my cut. I have 80 Newton meters acting that way, 20 Newton meters acting the opposite, 30 Newton meters acting this way. And finally, double-headed arrowhead is helpful for hitting these directions, right? T and DA acts that way, assuming positive. I sum torques, set them equal to 0. I've got 80 Newton meters acting one direction, also in that same direction, 30 Newton meters, and the torque in DA. And acting in the opposite direction, I've got 20 Newton meters. And it all sums to 0. So solving for TDA, I'm going to get minus 90 Newton meters. So all 3 torques came out to be negative in this problem. If you thought about the direction of the angle of twist, it is going to end up being negative, which means push your thumb that way, it's going to end up rotating this direction, which should make sense since most of the torques are in this direction, and that is considered a negative rotation relative to the fixed end A. Okay, we have our torques. We can substitute everything in now. There's one giant equation. Phi is 1 over jg times the sum of the torques times the lengths. In the denominator, we have our 1.571 times 10 to the minus 8th meters to the fourth. G was 75 gigapascals. That's 75 times 10 to the 9th newtons per square meter. And at the top, we're going to sum these things up. So the first segment was minus 80 Newton meters, which gets multiplied by its length, 800 millimeters or 0.8 meters. The next section had a torque of minus 60 Newton meters, which needs to get multiplied by its length, which was 600 millimeters or 0.6 meters. Finally, minus 90 Newton meters. These are minus because of the sign of the torque is negative. And this one had a length of 200 millimeters or 0.2 meters. This comes out to be minus 0.1002, and the units should all cancel out. I've got newtons per square meter times meters to the fourth, so this becomes newtons meters squared in the bottom, and the top is newtons meters squared, newtons meters squared, newtons meters squared. So dimensionless for angles means radians. And if we convert this to degrees, it's minus 5.74 degrees. We do that by multiplying by 360 degrees divided by 2 pi radians. And we solve that problem. I want to do one more example of this type of problem. And this one's a little bit more complicated. We are dealing with a single material that's steel, slightly different steel, so slightly different shear modulus than the previous problem. G is 77 GPa. They want us to find the angle of twist at point A. This section from A to B is a solid shaft that's 30 millimeters in diameter. From C to B, it's a different solid shaft that is 60 millimeters in diameter. And from D to C, it's actually a hollow shaft, 60 millimeters for the outer diameter. And for some reason, somebody cut a little hole in here. So it's got a 44 millimeter diameter hole in the middle. And we have lengths and we have torques. Still going to be the exact same governing equation. Phi is the sum of all the TLs over JGs. This time, the only thing we can pull out in front of the summation is the G, because J is going to be different in each of our 3 sections. So for each section, I need to find the torque, and I need to find the polar moment of inertia J. Turns out I'm actually going to need 2 free body diagrams this time. One of them for this little piece out here. Let's do that free body diagram where we cut in between A and B. So if I cut there and I keep everything in front of the cut, I've got a torque of 250 Newton meters that's applied. And then if you stick your thumb out that way, you would end up with an internal torque in section AB that's in that direction. And summing those torques, you get that TAB will have to be minus 250 Newton meters. The reason I only need to do one other free body diagram is you only need a new free body diagram when you've had a change in torque. So you will definitely need one either in between B and C or in between C and D, but it doesn't matter where in here I cut it, the torque doesn't change. J changes, but the torque doesn't. So why don't we just cut between B and C and do a free body diagram cut between BC. So here is my cut. Then we have a step down to a smaller shaft. Applied to it is 250 Newton meters that way. And then we had a big torque, 2000 Newton meters that way. And we'll, again, use our positive sign convention, which will have our internal torque in between B and C that way. If you sum those torques, you get the torque in BC comes out to be minus 2250 Newton meters. And we don't need to do a separate cut, but the torque in section CD will also be minus 2250 Newton meters. You just need to cut it every time the torque changes. So now I need J's for each of these. J for AB, pi over 2 times the radius to the fourth. That first section has a diameter of 30 millimeters. Radius would be 15 millimeters. I like to convert it into meters. So 0.15 meters. It gets raised to the fourth power. And this comes out to be 0.0795 times 10 to the minus 6 meters to the fourth. Your calculator won't give it to you that way. I just shifted my decimal a couple places over so that all of my J's would have the same exponent. They'd all be times 10 to the minus 6. Let's do the next one. Segment BC is also solid. So we do pi over 2 times the radius to the fourth. This one has a diameter of 60. Cut it in half, you get 30 millimeters. And putting that into meters, that will be 0.030 meters, which gets raised to the fourth. That comes out to be 1.272 times 10 to the minus 6 meters to the fourth. And finally, CD, this one's hollow. So we start with pi over 2 times the outer radius to the fourth, 0.030 meters to the fourth, minus pi over 2 times the inner radius to the fourth. 44 millimeters, cut that in half, you get 22 millimeters. Put it into meters, you get 0.22 meters to the fourth. And that number is 0.904 times 10 to the minus 6 meters to the fourth. We have all of the stuff we need. So now we just need to add them up. Phi is going to equal TL over JG for segment AB plus TL over JG for segment BC plus TL over JG for segment CD. I can pull the G out in front because that's common for all of them. So this is 1 over, it was 77 gigapascals, that's 77 times 10 to the 9th newtons per square meter. Now inside the bracket, first for segment AB, AB had a torque of minus 250 Newton meters. Its length was right here, 0.4 meters. We already have G out in front. I do need to include J. The purple J was 0.0795 times 10 to the minus 6th meters to the 4th. Next, we need the blue one. Torque for segment BC was negative 2250 Newton meters. I need to find its length on the picture. Its length was 0.2 meters. G is out in front already, so I just need J, 1.272 times 10 to the minus 6th meters to the 4th. And finally, the green one. Segment CD had the same torque, minus 2250 Newton meters. Its length was 0.6 meters. And its J is 0.904 times 10 to the minus 6th meters to the 4th. And all of that together comes out to be dimensionless minus 0.403 radians, which is minus 2.31 degrees. And we've solved another problem that has a negative angle of twist because all the torques were applied in the negative direction.